Okay, we're going to go ahead and get the highly anticipated flux session underway. Our first speaker is Mr. Tim Minnick. He is with Minnick in Soto in New Jersey. Is that like New York City, the New Jersey side, or basically?
Yeah.
Okay. That general area, it's about as John said, about the same size as Pinedale, not maybe a few more people. Anyway, Minnick and Soto, they specialize in combining optical remote sensing, air dispersion modeling, and meteorological monitoring to assess emissions rates. And Mr. Minnick also serves as a consultant for the New York Jets. So he's going to do his presentation first, and then we'll have Dr. Field come up. If we could give a round of applause to Mr. Minnick.
Well, I have to say the Jets is a hopeless cause after last week, so I'm going to strike that for the next time. So, thank you, Brian. The title of this talk is Measuring Methane Flux from Leaking Gas Pipelines in Real Time. Emission was established in 1996, and we provide specialized air quality and meteorological services to industry and government. We have particular expertise in air dispersion modeling and application of optical remote sensing to measure emission rates and off-site exposure from complex sources. We've designed and managed about 20 ORS-type projects from regulatory application over the years and a lot more for applied R&D. Our ORS-based clients include the Gas Technology Institute, US EPA Environmental Response Team, the US Army Corps, the New York City DEP, NACASI, and numerous A&E firms. So why use optical remote sensing to measure emission rates? Well, inherent in any ORS technique is the ability to collect data which are spatially representative of the downwind area of concern. And while we haven't said those words explicitly today, a lot of that has been implicit in a lot of the people's talks. You have to get a handle on how the spatial representativeness of your measurements, because air is such a confounding medium, as you well know. So I want to go over briefly here the method overview. E-Calc is our emissions calculation software which facilitates application of the area source technique. Now I'm going to talk about E-Calc in a minute, but I just want to mention what the area source technique is. It is a technique which quantifies the gaseous contaminant emission rates, which is flux, from ground level sources. And these ground level sources could be landfills, hazardous waste sites, lagoons, or oil and gas industry processes and pipelines. And it employs AirMod, which is the US EPA guideline air dispersion model. An emission rate, a mass per time emission rate, such as milligrams per second, is derived from the cross-plume path integrated concentration measured downwind of the source, and also together with the coincident on-site meteorology. We calculate an emission rate every 15 minutes. Now, for this application, the preferred optical remote sensing technology is tunable diode laser, although we've used open path FTIR spectroscopy, and we've even used point monitoring for things like hydrogen sulfide, which is not optically active. So we just take measurements along a path, and we just add them together and multiply by the path length to simulate a path integrated concentration. So, the tunable diode laser, and you've all been hearing about this all day, and I'm glad that we all picked a good vendor to talk about this, because it's, again, we're talking about the Boreal laser gas finder. It employs a beam of light which can be tuned over a narrow portion of the electromagnetic spectrum, specifically to the compound of concern, in this case methane. And the concentration is derived from the change in absorbance over several wavelengths spanning the entire methane absorption line. And the way we use it is, here's the instrument, here's a retroreflector. That beam of light gets reflected back to the transmitter and receiver. And that's how we get our path integrated concentration. Now, the area source technique is very straightforward conceptually. It really is remarkable in its simplicity, but the devil is in the details. It's really basically 3 steps. We start out with measuring a source attribution, and we call the last slide, the instrument is here, and there's a retroreflector in the back. This is your leak, this is an overview, this would be a gas pipeline, and here's your meteorology, and the wind is blowing like this. So you can see that we have the plume contained in this depiction here. So the first step is to measure that path integrated concentration with the TDL. The second step, this is where the quote trick is. Not really a trick, but you'll see. You just assume, for now, a unity emission rate of that source, like 1 gram or 1 milligram per second. That's the emission rate. Remember, a model, I'm sure most of you are aware that you start with an emission rate, and the model predicts the downwind concentration under that meteorology. Well, that's what we do next. We assume that emission rate is 1 milligram per second. And we say, okay, we then predict the downwind concentration every single meter along that path length. So if this path length is 200 meters long, we model 200 different point locations. And since they're only a meter apart, that's more than adequate to just sum them up, multiply times 200 meters, and that becomes your path integrated concentration. So what that says is, if your emission rate really was 1 milligram per second, under that 15-minute meteorology, that's what the instrument would see, okay? But it's not 1 milligram per second. We don't know what it is. But now we have an equation, a relationship where we have 3 knowns and only 1 unknown. The only thing we don't know is the actual emission rate. So, step 3, calculate the emission rate Q per the equation below. The actual emission rate Q is equal to the unity-based emission rate, which we already said was 1, times the quotient of the measured path integrated concentration, C, divided by the unity-based path integrated concentration. And that's it. That's all that it is. The trick, though, of course, is AirMod is not a simple model. It's a pain in the you-know-what. But anyway, that's how it works. So again, just reiterate real quick. You simulate the emission rate, you 1 milligram per second, you predict all along the actual measurement path, and then you use that relationship to back calculate the actual emission rate, because now you know your actual measured concentration. Now I just want to point one thing out. You can see from this depiction that the length of the beam path is long enough to fully encompass the plume, okay, for this depiction. But that's not always the case. A lot of times you don't know if you have the plume contained, especially if a leak is large or you have a large source. I just want you to keep this picture in mind, because we're going to come back to that in just a second. So now I want to talk about the E-Calc. This is our emission software. It's based on application of the area source using AirMod. AirMod, as you know, or maybe know, is a model that's in the public domain. We don't have any, there's nothing magical about AirMod. It's an EPA model. It happens to be the best model. So we use AirMod, and most data is entered manually on input screens, which I'm going to show you. And in order to maintain AirMod's legal status, E-Calc employs the model's regulatory version. Therefore, all E-Calc results are technically defensible and legally admissible. So this is, it's hard to see this, but I don't want to get too specific anyway. This is a sample E-Calc menu and some of the input screens that's required. And all I want to say about this right now is that you enter the monitoring configuration data in this screen, your emissions calculation information, characterization information in this screen, and you enter a lot of the information to generate your E-Calc input information here. And this is really the workhorse of the way we set this up. This information, and this is an actual screen from a project we did in California, which I'm going to talk about in just a second. This is the project information. In this case, it's the South Coast Air Quality Management District. The event information, the measurement identification, all the meteorological information that's necessary to run AirMod gets entered on those screens, and it shows up here. And this, you'll remember, this is that same equation that we saw before. All these values are known except Q, which is what we're after. That's the emission rate. And now, this is something that's really cool about the area source technique. This is the plume capture equation. Remember I said that we don't know if we've got the beam, if we've got the plume fully contained in the beam. And remember I said you do the unity-based modeling, and you set up the receptors all along that path length of the measurement, right? If it's 200 meters, your path length for your unity-based modeling is exactly 200 meters. But in order to show whether or not you've got the plume contained, what we do is, it's very simple. We extend that unity-based modeling receptors, maybe 100 meters or 200 meters in each direction, so that if the plume is contained, C sub U, which is the concentration path averaged along that path length, the unity-based modeling, C sub UE is the extended path length. If it's contained, that's going to be 1. But if you don't have the plume fully contained, that's going to be a fraction. And that tells you how much of the plume we've got contained in the beam. And the beautiful part is, it already compensates for that. But it's nice to know, because we usually set criteria. 70% we need for plume capture, otherwise we say it's not valid data. So, anyway, it's pretty cool stuff. This is a sample report. We generate a report. It can be printed out every 15 minutes, and there's one report for each compound that we monitor. We've used OpenPath FTIR a lot, so that's why we can do multiple compounds. Okay, so I want to just briefly talk about some validation work we did recently. A 2-day field study in Texas. We used OpenPath FTIR to measure controlled SF6 sulfur hexafluoride releases from surface locations approximating or near a compressor condensate tank complex on day 1 and from gathering gas pipelines on day 2. 4 continuous 15-minute events were conducted on day 1 and 16 on day 2. And emission rates were measured using E-Calc and then compared to the known or controlled emission rates for SF6. So this is where we were. This is the SF6 release location for day 1. This is where the condensate tanks were, right here. Now, we couldn't get on them, certainly not, but we were actually on a berm which was at the same height as the top of the condensate tank, so we figured that was, very representative of the location. And this was our beam path on day 1. And on day 2, and the Met Tower, both days were here, it was there. And on day 2, the SF6 release location was here to simulate the release from the gas pipelines, which were right there, and there's the beam for day 2. So you see the layout. And this is a picture of the condensate tank and the layout of that work. Okay, so, sorry. Day 1, remember we had 4 events, and this is the actual is the straight across line, the darker one, and the predicted was that. And this is for day 2, the 16 events to simulate the gas gathering pipelines. You can see, we're not showing statistics here, but you can see how really close we came to getting the actual emission rates. Okay, so another study we did in the fall of 2015, there were 4 international contractors participated in a 6-week study for the South Coast Air Quality Management District to do some R&D work to figure out which is the best optical remote sensing approach for measuring emissions from refineries, shipyards, and small industrial sources. We were part of the United States team, and our work was only 4 weeks long. But we used E-Calc with OpenPath FTIR this time to measure emission rates from gas stations, oil wells and tanks, and cattle farms in Los Angeles basin. And over those 4 weeks, we actually had 185 valid emission rates, 15-minute averages, with up to 12 contaminants. Not all the sources had 12 contaminants, but there were a total of 12 different contaminants that we measured. And we had, there were 17 gas stations, 16 oil wells, and 2 cattle farms. I say this because it illustrates the method is very easy to implement, and it's very economical. It really, we were sometimes able to do 2 or 3 sources a day. Other days we had bad weather, but that's what we were able to accomplish. There's a picture of some of the oil and gas well activities and sites that we were measuring. And so, next quick. E-Calc, in conclusion, E-Calc rapidly quantifies methane emissions from leaking gas pipelines or other sources. Now, it seems like a real good, everything we've heard today, we heard about, top-down views to find the location generally of leaks. We heard about, the vehicles that come out there and actually locate the actual leaks. And if you don't need to quantify the emissions, you can stop there. It's perfect. But if you do, you can just immediately go to the site and you can set this up and you can run. So if you want any technical papers or reports on the studies I've talked to, just go ahead and email me or phone. But thank you so much.
Yeah, if you do want to get in touch with Tim, we can help you out with that as well.